starting. Okay, so what have we done so far? So we understood one thing, something called a scalar field. Okay, scalar
field.
field. Okay, so what is this scalar
Mm.
field? Field means field is defined in a coordinate system. Okay,
Mm.
1D रे in 1D the coordinate is only x, in 2D it is xy, in 3D xyz, in higher dimension there are many coordinates. Okay,
Mm.
so scalar field means, so it's a function of the coordinates xyz. Okay,
Mm.
so this is a Cartesian coordinate and the value of rho depends on where we are. If you give me the xyz coordinate, there I can tell what is the value of rho. Okay,
Mm.
so what is the meaning of scalar field? Then the scalar field is defined on a coordinate system. Come answer. The scalar field is defined in a coordinate system. Okay,
Mm.
it has only magnitude. It has only magnitude. Okay, that depends on the position. Okay, on the coordinate system. Okay,
Mm.
system. Okay,
Mm.
very good.
Mm.
So there are some standard, you must have read this electric field. Electric field is a vector field. Okay, but
Mm.
the electric potential कौन
Electric potential.
potential is a what, is a scalar field.
Mm.
Okay,
हाँ.
so if you are in 3D, you know, if you are in 3D, there is a charge, let's say charge is at origin. Okay,
Mm.
so in origin there is a charge q. Okay,
Mm.
so due to this charge there is a potential field everywhere in the space. Okay,
Mm.
so what is this potential field? As a function of r, it is k, where k is the dielectric constant, q by r. No?
Mm.
So this is a spherical coordinate system. If you convert to a Cartesian coordinate system, this will be xyz, this will be k q by x square plus y square plus z square root over k q by
Mm.
r. Okay,
हाँ.
so this is a potential and this is scalar field. So what is the vector field then? What is vector field? You tell.
16 by 5.
Same as scalar field. Okay, same as scalar field, but has a direction. Okay,
Mm.
so I'll say E vector as a function of x, y, z. Okay,
Mm.
so example, in the same example, if you go to a spherical coordinate system, okay,
Mm.
so this is a spherical coordinate system, so there is a charge q at origin. Okay,
Mm.
due to this charge there is a electric field at some position r. So what
Mm.
is the E vector? As a function of xyz, Due to Coulomb's law, this will be kq by r square into r cap vector, where r cap is the unit vector along the r direction. Okay, understood? Any problem? Now we'll go to from spherical coordinate to a Cartesian coordinate. Sorry, I wrote x, y, z. It should be what? R only. Okay. So E is a function of R. So now we can make E to the Cartesian coordinate x, y, z equal to kq by what is r square?
X square y square plus z square.
X square plus y square plus z square. Okay, into r cap. R cap means r vector by r vector.
Magnet.
R vector by r vector magnitude. Okay. So unit vector is vector by vector magnitude. So that becomes kq by x square plus y square plus z square to the power 3 by 2. Okay, this is 1, this will be square root 3 by 2. And what is r cap? R cap is x I cap y j cap plus z k cap. So this is the whole story. Okay. So you understood what is the vector field and what are the scalar field. Okay. So then we understood one more point. Then we understood one thing, Nabla operator. What is this? Nabla operator. Okay. What is that? So in class 11 12 we have encountered multiple operators, like integration is an operator. Okay.
Oh, mouse.
Derivative is an operator. Okay. So the operator acts on a function only, f of x dx. Derivative operator acts on a function, f of x. Okay, similarly Nabla is an operator. Okay. Nabla operator is this in Cartesian coordinate. D by dx I cap, d by dy j cap, then k cap. So Nabla is a vector operator. So as it is a vector operator, so it can act on vector and scalar in a different way. Okay. And vectors have this dot product and cross product. So if I just apply a Nabla with a scalar field, Nabla on a scalar field. Okay. So let's say Nabla acting on a rho xyz. Simple. What is the issue? So this is called a Nabla. If Nabla is acting on a scalar, we will say it is gradient. What is?
Gradient. By divergence with the formula same.
Gradient. Yes. So this will be this. So d by dx rho of xyz partial derivative with respect to x into I cap, then partial derivative with respect to y with j cap, partial derivative with respect to z with k cap. Okay. So this is gradient. This is just gradient. What is the meaning of gradient? What is the physical significance of gradient? Okay. So you understood gradient is something, but what is the meaning of gradient? As I have said already. So you have a scalar field. Okay. Hello. So scalar field might look very complicated. So simply do 1D scalar field. It's just a, let's plot a function only. V of x half kx square, let's say this function I want to plot.
Hmm.
Okay, so it is plotted x equal to 0 रे 0 और सब बड़ा पॉजिटिव होगा, so this is a parabola. Okay, so this is a function. So if you apply a gradient operator at any point, any space, so this will gradient acting on a scalar will give a vector. Okay, so this vector will always point towards the vector, means it has a direction. So this vector will always point towards the direction that try to minimize the function. Okay,
Hmm.
gradient, what the physical significance of gradient? It always the direction, the direction of gradient of a scalar field is towards the minima, local minima, local minima. Okay,
Hmm.
so gradient will tends to the local minima always. That's the gradient. That's all about gradient. You just have to understand the definition of gradient is this much and what is the physical significance. Now I can say, okay, find the gradient of some function. Then that's not a interesting thing for you, because question, if I say, okay, find the gradient of f of x y z, yes, I'll say simple x square plus y square plus z square. So this is a scalar field.
Hmm.
Is this a scalar field? Why? Because it depends on the coordinates x y z and it has no direction. So this is a scalar. So this is a scalar field. So if I apply a gradient operator on this, gradient on f of x y z, okay, you know, anyway, my job is to do it. 1 second. dy dx x square plus y square plus z square j cap dy dz x square plus y square plus z square k cap. Okay, so do partial derivative with respect to x, you will get 2xi cap 2yj cap 2z k cap. Okay, that's it. Depend on the value of x y z. Somebody asks what is the gradient of this function at this location. So first we will find the derivative, then we will put the value x y z. Okay, so after gradient the next thing is what? Divergence, right? Divergence is exactly same as a gradient, but it acts on a vector. So that will be dot product. Otherwise, how will it act on a vector? Okay, this is a dot product. This has to be a dot product or a cross product. Okay, simple. Now we know what is gradient, what is a vector. Let's say my a vector is equal to some ax, which is a function of xyz I cap, ay, which is a function of xyz j cap, az, which is a function of xyz k cap. Okay, now if you apply the dot product, you write gradient as divergence with respect to x I cap, divergence with respect to y j cap, divergence with respect to z k cap, and you dotted with what? A vector ax, which might be a function of x y z I cap, ay. What are x, ay, az are the component of the vector along x direction, y direction and z direction. Okay. Are you getting my point? Hello?
हाँ.
Any doubt so far? You do the dot product, you will get this ax, xyz, dy, dy of ay, xyz, dy, dz of az, xy. Okay?
Hmm.
Very good.
Hmm.
Very, very, very interesting stuff is going on. Now the divergence of a vector field is a scalar. This is a scalar function. There is no direction associated with this. Now we understood what is the divergence, how divergence acts on a vector. But what is the meaning of this? The meaning is, what is the meaning, can you tell? No? The divergence of a vector field always gives the information about source or shrink. Okay? So what is that? What does that mean? So let's say this is a electric field due to a point charge. Okay?
Hmm.
So this is the 3D thing, and you have a vector field all over the place. The vector is there. Some vector somewhere. Vector is there. So this is a point charge is here. So we have a point charge here. So due to this point charge we have vector field all over the place. Right?
Hmm.
So it will look something like this. So if you find the divergence of this field, divergence is defined in every space point, every xyz. So you can calculate the divergence all over the place. You will get zero everywhere except origin. You will get a finite. Okay.
हाँ.
So if you just find the divergence of this electric field, you will get just q by epsilon. Oh, this is the Gauss law. That's a different story. Okay. So
Hmm.
this E is a function of xyz, but the right hand side is the only at origin. So divergence of a field, vector field, gives the information about the source where the field has emerged. Okay?
Hmm.
Did you understand my point? What I am trying to say? Okay?
हाँ.
Any issue? So you understood divergence, gradient. Then the next thing is what?
Cos.
Curl. It's a curl. Curl. So what is that? Because the nabla is a vector, so it can act on a vector field different way. So this is cross product. Okay? Do you remember how do you define the cross product between two vectors?
हाँ.
So do
Mid
this.
terminal.
I J K AX AY AZ. Okay? BX BY BZ. Okay, A cross B is equal to this much. Same game we will play with the Nabla operator. Nothing fancy. Hmm?
Hmm.
So So the nabla cross with a will be equal to I cap, j cap, k cap. Nothing fancy, just you need to remember the rule and apply. Just remember what is the meaning and how it works. That's all. This is the diversion curl. Okay. Now you'll ask what is the meaning of curl. That's the interesting part. So curl will curl of a vector will give the information about vertex. Okay. What is vertex? So this is, let's say, pani, water. Okay. Simple. Very, very interesting. So this we have this. We have a river channel. In that river, water is flowing. What is flowing? Water is flowing.
Yeah.
Oh my god, what happened to my... Let's say this is the pani. But the pani might not flow this way. So might be there is some circle. Okay?
Yeah.
Oh, this sort. So these are called vortex. Some circle. Okay?
Yeah.
So this velocity field of the river, this is a 2D vector, xy. Okay?
Yeah.
So these are this rotational effect. It is rotating at some point. So the curl will decide this. Okay? So everywhere, all over the place, it will be 0. In this location, it will be finite. Okay?
Yeah.
So you understood gradient, divergence, curl. There is another thing that's called Laplacian. What is that?
Laplacian.
Laplacian. C and okay. This is a funny object because it can act on scalar and vector both. Gradient will act on scalar only. Divergence will act on vector only. Curl will act on vector only. But the Laplacian can act on both things. Okay.
Yeah.
So if it acts on scalar, it gives scalar. It acts on vector, it gives the vector. So it defines like this. This is del square. Del square means del nabla dot nabla. Go to nabla dot. So this will be d square dx square plus d square dy square d square dz square. This is operator. You can act this on a scalar field. Okay.
Yeah.
This will be this rho xyz plus d square by dy square rho xyz plus d square by dz square rho xyz. Okay.
Yeah.
Similarly, you can add this nabla operator on a vector field. It's an electric field E xyz. It will give just this. Same thing with a vector sign E vector again. D square by dy square E vector. D square by dz square E vector. Okay.
Yeah.
The meaning is slightly complicated at this point. I don't want to tell. You'll understand it later. Okay. So far, I'll stop for some time at this point. We'll continue further.